17th of December 2021. This is the last lecture in the series on Lattice Boltzmann method for the year 2021. And this lecture is a little bit different from the previous lectures insofar as we are not studying a lot of theory today, but we have the implementation challenge where we try to implement a Lattice Boltzmann code during the lecture. So this is quite challenging. I have a sheet, but still we are dependent on that I don't have any typos. Okay, we will implement our Lattice Boltzmann code in Mathematica here. This is probably not the way you want to do your homework, because the code that we are implementing will be the slowest Lattice Boltzmann code on Earth. This I can promise you. However, in Mathematica, we can use the computer algebra functionality to also do the derivations while we implement our code. So, okay, obviously we will implement a two-dimensional code, and this will be, of course, in our we'll use the D2Q9 lattice, and we will use Bgk collision operator. Yeah, this first leads us to the problem that we have to get our equilibrium function. So of course we derived our equilibrium function already during the lecture, and we could now just type it, but we do it the way we did it in the lecture. We get the equilibrium function from the equilibrium moments. So the equilibrium moments MEQ, yeah, and they will have the indices A and B. And here we first define the moment 0, 0, M0, 0, given a velocity u. So this is now a function given a velocity u. No, wait, I already mistyped. Given a velocity u and v and the density rho. So this we define as, so this is the zero moment. The zero moment obviously is a conserved moment and is equal to rho. So this is the definition of the zero moment. Then we have the two first order moments, MQ, so 1 and 0. This is of course a function of u and v and of rho again. And this is equal to, yeah, what is it equal to? It is equal to rho times u, yeah, because it's the x velocity. So now I can actually copy this, make it big quicker. So I want to have the moment, the momentum in y direction. This is rho times v, so this is the first moment in the other direction. And then we have the second moments, m2, 0, and this into u. I mean, this is dependent on u, v, and oh, I made a mistake. I just recognized this is a function. So, okay, if you're not familiar with Mathematica, it's is not so important to be familiar with everything here, but if we specify arguments for a function, we will have to put this blank here. Yeah, otherwise I would have mistyped this. So okay, the second moment in x direction, so m equilibrium to 0, which now is of course not a conserved quantity anymore. Don't forget the blank. This is now defined as, according to the lecture, rho times u square plus theta. Yeah. Okay, and obviously the other one, 0, 2, being defined as v square. Okay, now we have, out of our 9 moments that we have 1, 2, 3, we have 5 moments defined. And what we do for the other moments is factorization, of course. Yeah, because in the lecture we already said that the equilibrium moment MAB equilibrium can also be written as the equilibrium of MA0 times the equilibrium of 0B moments divided by M00, and this is what we are going to apply for all the other moments. And we use the feature in Mathematica. Oops, now I'm in the wrong space here. Where's my cursor? Here. Okay, so in Mathematica we can use function overloading. This means if instead of giving these explicit indices 0 or 1 or 2, we can also give here a pattern, yeah, a pattern that will be recognized as anything that has not yet been defined before. So these are now the moments that do not fit in the previous definition. So when a and b is not equal to 0 and 1 and 2, then this will of course have the same pattern here, rho. Well, and yet by definition, as we said, this is M equilibrium. Now, oops, this was the wrong one. A, not blank, A and 0 times M equilibrium 0 and B, and obviously I've forgotten to give the V, U, and and rho. Yes. So, and then why do I write V, U, and rho? I'm stupid. So if I misbehave today, I got my booster shot of the vaccine yesterday, and I recognized every time. So it's the third vaccine, and it it becomes more and more effective with regard to the, I don't know, side effects I recognize. Okay, so this divided by M EQ, the zero order moment, so the zero order moment is M EQ 0, 0, and this of U, V, U, V, and rho. with rho. Okay, so this gives the definition of the equilibrium moments. Well, for the Bgk, of course, what we need is the equilibrium distributions, yeah, because Bgk, as you know, gives us the post-collision state of I, Fi, now it's Fij, it will be Fij, yeah, for the different directions. For example, this here is F1, 0, and this here is F minus 1, 0 is actually visible, right? So, and so on. So this is 0, minus 1, and this here is F 0, 1, and so on, yeah? So, okay, how does this work? We have an Fij before collision, 1 minus an omega plus Fiq equilibrium times omega. So this is Bgk, right? So now we have the equilibrium in terms of moments, and what we actually need is the equilibrium in terms of distributions. So first of all, we have to tell Mathematica how we connect moments with distributions, and for this we define, I don't know whether I got here, I have not executed this, I believe. So we define moments, so these are now not equilibrium moments, but they are arbitrary moments, so they are also dependent on A and B, yeah. And our definition of the moment is of course the sum over I and J, and we sum T. So, and we start here from I equals to minus 1, and this goes to 1. So I delete this, and we have to write another sum here. So that goes from J equal to minus 1 to 1. So what was this? Okay, so this, I killed this. Sum. So now it's J from minus 1 to 1, right? So, and yes, so this is here now the distribution F, I, and J times I by the power of A plus, no, not plus, times J by the power, this was the wrong button, oops, by the power of B. Okay, so we can try this out and let us see whether we can actually get a moment M, say moment M1, 1. So what we get is, yes, this is the moment M11. So this is the distributions F minus 1 minus 1 minus F minus 1 1 minus F1 minus 1 plus F1 1. Okay, so this is actually correct. However, there is a problem here with this definition. So unfortunately, yeah, we have in this definition, we have a little bit of problem, and here, because we are programming it, We have to be accurate. So the problem is that if both, say J and B, are 0 at the same time, yeah, then we have 0 by the power of 0, and 0 by the power of 0 is not defined. So this is a problem in programming. So we have to actually cheat here in order to make the definition. So the thing that we want to define is that 0 by the power of 0 is equal to 1. So this is just our assumption here. This is the one that works. And this in Mathematica will be done. I experienced the first technical problem now. What is wrong? Okay, so this can be done in Mathematica. Oops, something. Okay, sorry, I have a small problem. What did happen? How did this happen? Okay, sorry. Sorry. Okay, so what we are doing is we add some cheat. Yeah, we say I plus cheat by the power of A and J plus cheat by the power of B. So because we have not specified what cheat is, so when we take this to the power of 0, it will interpret this as 1. Yeah, so because something by the power of 0 is usually 1, unless there's something is 0. And actually, Mathematica is here not quite correctly implemented, in my opinion. But we can cheat our way out of this. So if you don't understand this, this is not so important. What we can do in Mathematica, because it's a computer algebra system, we can do a substitution here. So this slash dot just means a substitution, and we say, okay, there is this cheat in here. Then we apply the sum, and afterwards we replace the sheet with 0, and then everything should be fine. And let's see whether this actually works out. Fine. Okay, so this is how we want to define it, and unfortunately we have to do this cheating here a little bit. Okay, so now we have the definition of distributions. But what we want to have is the equilibrium. So we have to define an equilibrium, F equilibrium, that I now define as a table of these equations, and use the computer algebra system to actually solve these equations. So what we like to do in a computer algebra all the time is to simplify our results. So we pipe everything through simplify. Yeah, this is not important, but we will speed up the code later. Then we say solve. So we want to solve all the equations from the moments to the distributions. So which are these equations? We have to do some housekeeping from Mathematica. So there is a function that is called flatten. What this is not very important. This just regulates the lists in the table of equations that we will now generate. So we generate a table of equations for all the different moments in equilibrium A, B, yeah, which are of course functions of u, v, and rho. This means we're calling these functions that we have up there. Have the debugger on. I don't know how to turn this off. Please. Okay, I don't know how to turn this off. I hope this will not slow down the code more than. Okay, if somebody finds out how to turn off the debugger in Mathematica, please tell me. So this is equal to, yeah, we have now a set of equations, and we specify equations by double equal signs. So this is equal to m, this is equal to the definition of moments. Yeah, so the moments MAB, yeah, are now set to the equilibrium, and what we want to have is of course the distributions that correspond to this. So we have to specify the table of equations. So what is A? A goes from 0 to 2. Yeah, so this is the moments 0, 1, 2. And also in B from 0 to 2. Okay, so now we have to close all our brackets, and then we have to tell the code what we want to be solved for. Again, we need some housekeeping by doing this flattening of the table. And here we give the variables for which we want to solve, and the variables we want to solve for is of course the distributions f, I, and j. And there's the same number of equations, but they are going from -1 to 1, and from, j, I from -1 to 1, and j of course also from -1 to 1. So, and once we've done this, we replace f by by a new variable that we call ff equilibrium. Okay. So what happens? It doesn't work because I mistyped something. Flatten table. Yes, I did not close these brackets. And this has to be a substitution. So we substitute things by specifying that f will be substituted to f equilibrium. Okay, so and this is now the solution for our equilibrium function. Yeah. Okay. We could have known this beforehand and typed this in, but this is what we can actually derive using Mathematica. Okay, I'm going to save this that we don't get lost. Now we are done with deriving the equilibrium. Now we have to specify a simulation setup, and of course we are a bit concerned with your assignment. And what we are going to do is we specify a small body here, yeah, where we say here we get bounce back, and everywhere else, which is probably not the very best solution to this, but because we have only so much time, we will do it as simple as possible. We'll set everywhere around the system, we are going to set equilibrium boundary conditions. So this is what we had last lecture. Yeah, bounce back and equilibrium equilibrium boundary condition, and we'll set the equilibrium boundary condition as an inflow going into the domain, so that the flow is coming from the left and is going to the right. Okay, so this means we're coming here to simulation setup. Now, as I said, our code will be extremely slow because we'll implement it directly in Mathematica, and also the debugger is turned on and I cannot turn it off. So we specify a very small domain, yeah? So we need to specify the length of a domain, Lx and Ly, and I'm going to say, okay, this is, say this is 40 lattice nodes, 40 delta x, and this here will be 30 delta x. So we'll make this relatively small. I'm always forget that I have to, I have some problems with my mouse. Okay. So this is Lx equal to 40, Ly equal to, I said 30. Yeah, so then we have to also specify some other things like the velocity. Yeah, this I call u0. The velocity I set to 0.01. Yeah, lattice units, of course. We have a v0. V0 I set to 0.0. We have a rho 0 density. So important, the density must not be 0. The density must, otherwise we divide by 0. Yeah, that's not good. So this is, we usually set this to 1. And then we have to specify the size of our obstacle that we want to specify. I'll give this obstacle. Okay, I say this is this has a size of four lattice nodes in each direction, and of course, because we want to run Bgk code, we also have to specify our omega, yeah, and so I just give now an arbitrary number, omega equal to 1.9, yeah. Okay. Now we have to make our setup. So of course we have to specify the variable where we record our distributions, yeah, and this we call now ff. And this we generate again as a table, which we want to initialize. So we have to also initialize it, and the way we initialize it is by using the equilibrium, where I just recognize, okay, let me briefly do this. EQ, I and J, U0, V0, and rho 0, and this of course for I equal to -1 and 1, and from J again from -1 to 1. So, and this is now supposed to be a field of distribution, so we also have to specify this in x and y coordinates. So I said this is nx, yeah, nx goes from 1 to lx, so the length of the domain, and also the height of the domain, so ny from 1 to ly. Okay, and then I have to do something else. I have to add that we need 2 sets of distributions. So why do we need 2 sets of distributions? We need 2 sets of distributions because we have, of course, we have the post-collision state and we have the pre-collision state, yeah? And what we are going to do is we call one of them A later and the other one B, and we write from one to the other, and then we switch the state. So we need 2 distributions, yeah, because we have the pre-collision and we want to write the post-collision. So, and I called this here odd because we will switch this in odd and even time steps. So if this would ever my mouse worked. So the problem that I just recognized is that I use the function here which I previously didn't define. So I think I still have to define this, and I do this up here because this still is part of the equilibrium thing. So this FEQ I and J of, okay, I will use a little bit different names, and rho, yeah, so these are the incoming, this I define as FFEQ, so FFEQ is the thing that comes into the FEQ, this capital FEQ up here, which again has the indices I and J. So then we do a substitution. As I said, this /dot means substitution of FEQ, the first element. So this is not important, but this somehow belongs into Mathematica. And then we again do a substitution with the U that we find there by UU and the V that we find there by VV and the rho that we find there by rho. And okay, so we'll also specify here that theta is equal to 1/3, yeah, because so we don't need this later. Okay, this has to be specified. So, and then in addition to these storage for the distribution, we also need storage for the macroscopic quantities that we want to have, namely the density rho. Yeah, we tell this is a table for rho, and we initialize the thing with rho 0, so there starts from this initial condition, and this has of course the size Lx and Ly, which we specify by saying nx goes from 1 to Lx, and ny goes from 1 to Ly. Okay, so, and now we have to do the same thing also for the two velocities, because we also want to save our velocities somewhere. So this means this would here be u0, and this we plug into u, and then we have v, and this goes with v0. Okay. Okay, so now since we are dealing with a geometry in our system here, we also need to specify the geometry, and this we do by, that's again the same problem with the cursor. I'm never touch the system. Yeah, it comes. Okay. So we specify another table of the same dimensions, which we call geo, and we call this, we again make a table, and we initialize this with something that we call bulk. So bulk is not anything defined. This is just a placeholder. Bulk, so bulk is where we have the usual fluid, the bulk of the fluid, and this of course has the same size as the previous lists, and y is from 1 till Ly. Okay, so, and this we now want to fill, yeah, and as I said, we want to specify the boundaries up and down and front and back, both, all four of them, with equilibrium boundary conditions. So we specify here, we make a for loop for xi equal to 2 and xi smaller than Lx. So we keep a little space outside, and xi plus plus, this goes into geo xi and 2, so geo xi and 2, so this is the lower edge the lower edge here. Yeah, unfortunately, every time that I draw something, I have problems going back to the file, to the code. So I should stop drawing. Yeah, so this is the lower line here. So I have to so two. Okay, we use two of these brackets to address a specific point in the array, yeah, here in Mathematica. So these are boundary conditions, and we set them to equilibrium, yeah, so we specified this is equilibrium. And we also do the same thing at the upper edge of this, so this would be Ly minus 1, so this is the upper edge. This is also the equilibrium, and this closes this one for loop here, and then we have another for loop for front and back, so this will be over yi equal to 2, yi is smaller than Ly yi plus plus, and this goes into geo 2, no, not like this, so geo 2 yi, and this is again equal to the equilibrium. And also for the back end, the back of the domain is Lx minus 1 and yi, and this is also equal to the equilibrium, and this closes the next for loop. So, and this gives us the outer rim of our domain, and now we have to specify the actual geometry, so the object that we place here, and we make a simple block geometry. Yeah, so you can specify other things here. We just said we are going from Lx divided by 3, and if we want to address an array with this is very dangerous, because if Lx, so 1/3 of the length of the domain, if this Lx is not an integer, we cannot use this for addressing. So therefore, to avoid this problem, I use the function floor, which is just rounding this to the next lower integer. Okay, and then we subtract here our obstacle r, so the radius of the obstacle, and we say that xi is smaller or equal x. Okay, this could, in this case it actually doesn't matter, because okay, obstacle plus obstacle r, xi plus plus. So now we want to have a square thing, so we have to do this also in the other direction. Floor. Now I put it in y direction. I'm going to put this in the middle, so by Ly divided by 2 minus obstacle r and yi smaller or equal to Ly2 plus obstacle r yi plus plus. So this is how we write the loop. And here we set geo of xi and yi. We set this to bounce back. Yeah, we call this bounce back, and then we close all our loops. So let us see whether this actually executes. So apparently this executes. So now we have the setup of our system. What we need next is that after we have a simulation, we also want to store our data somewhere. And this is pretty simple, but it has to be done. So we define a time series for row t, which is a placeholder for where we store our data for the density, which now is empty because we have not yet run it. ut again, and vt also empty. So this is where we store our results. And now I save. Okay, so this brings us to the actual thing that we want to do, namely writing our Lattice Boltzmann code. Okay, so we've half through with the time, and we have not started with writing the Lattice Boltzmann code. We will define a function, run LBM, and we'll define it like this, that we have something that I call out steps. Yeah, this is the time steps. This is the number of steps where how many times I will write out my data for post-processing, and then I have another steps, and this steps is the number of lattice Boltzmann steps that I do in between each time that I write out the data. So lattice Boltzmann uses relatively small time steps, so it's not useful to write out every time step. Otherwise, it's going to be too expensive. Okay. So now what we do in Mathematica here, which again is not very important, is that we define a module where we give all the, where we specify all the local variables first. Yeah, so I need some variables that I call step A, and I put this to equal to 1, and step B, which I put equal to 2. I need a row, I need a set of velocities, so this was wrong. I need velocities, u and v, and then I need a few variables for counting, I and jj, and I need a time for counting the time. I need a time for writing out the steps, and I need position counters m in x and m in y. So these are my variables, and then I have to have several for loops. So for t out is equal to 1. Yeah, so we have the outermost loop. T out is smaller or equal to out steps. Then we do t out plus plus. And then we have the inner loop for t equal to 1. T is smaller or equal to steps. And here we have t plus plus. Okay. So this t only counts the time steps in between each time that we write out if we do the write out. So I just recognize, so from the blue color I see that I mistyped this. This must be steps, yeah. Okay, so now these are the outer loops. So what's the first thing that we are going to do in the loop now is to generate our density and velocity fields. Yeah. In practice, this is not necessarily the fastest way of writing such a code, but I mean, there's a fast way to write the code, but it's not the fast way to run the code. But here is, yeah, for simplicity, what we do at the beginning of a time step is to compute the density and the velocity for all the nodes. Yeah. So, and here we start with the density, and the density is of course the zero order moment, m0, 0. So, and this I substitute, so m0, 0 is defined as a function up there, and I substitute the distributions in this function by f, I, and j, which I replace. So this is also a replacement operator with ff I plus 2 and j plus 2. Okay, so why I plus 2 and j plus 2? So you know that I goes from -0 to from -1 to +1. However, we cannot address an array in Mathematica from -1 to +1. It always goes from 1. The indices always start from 1. So we have to shift the indice. Unfortunately, we have to shift the indice by 2, and this I do by adding to I2 and to J2. Okay, so this will now happen in the other cases too. Then we go over nx, ny. We do this, so we have to extract the one of the two arrays that I specified here is as A and B, and we take the array A in this case, and we generate this over nx from 1 to lx and from ny 1 to ly. Okay, so this is supposed to generate us a table for the density, and the table for the velocities looks the same. This is why I'm just copying it. So we take here u and we put here this 1. I'm just recognizing that I made a mistake here. Because I still have to divide this. Yes, okay. Okay, so this has to be divided by the 0 order moment, of course. Everything else is fine. Right. Wait, this is not efficient. I make this more efficient by saying that this is equal to rho at the same location. I hope this is not going to kill me now. Nx and y. Okay, I hope this is... This is not on the cheat sheet. Okay, so this should give us the density and the velocity. So, and now we have to process our nodes, yeah? So we have 2 loops in x and in y, and we start this, so we skip the outer rims of the domain. So we start from m equal to 2 and mx smaller than lx and mx plus plus, and now also the same thing for my equal to 2, my is smaller than ly, and my plus plus. So now these are the 2 loops in space. And now we have to process our nodes with regard to what they are. Okay, so we have to distinguish between the different geometries. So we said that if the geometry of mx and my is equal to bulk, so if this is a bulk node, we apply our Bgk operator. So now how does the Bgk operator looks like? So the Bgk operator is again a function over the a loop over all the different directions, and because we specify the directions in x and y differently, we have to make 2 loops. Yeah, so we make a loop over ii that starts from -1 and is smaller than 2, and this will have to follow by a loop over jj from -1, jj smaller than 2, and jj plus plus. So, and now comes the Bgk operator. Yeah, the Bgk operator, the name of our distributions is ff. We go into ii plus 2, yeah, because we have to have this shift, jj plus 2, and now mx plus I, I'm going to explain this in a minute, my plus jj, and we now use the step B, so we use the data set B, and this is equal to FEQ II, so the equilibrium comes FAJJ IIJJ of U mx my v mx my and rho at the position mx and my. So this is the equilibrium. So I've written I've written it in a different order here, so I will give here an omega. This goes into omega times F equilibrium, and then we actually have the pre-collision distribution. Yeah, the pre-collision distribution looks similar to this post-collision distribution that we've written here. So I just copied this times 1 minus omega, and this plus this here. So there is a small difference, namely, so there's two differences. First, I have to subtract this guy here, and now we get this from the set A. So why do I add this mx? So that the new position mx is plus II and my plus jj. So what I'm doing, and now I have to go back to the slides here, is what we call push. Yeah, so we have to do the streaming and the collision, and what we do here is we combine streaming and collision. So for f I and j, yeah, we say that the new pre-collision fi and j at the position n, or what did we call it, m, yeah, m doesn't work, mx plus I and my plus j, and at the next time step, so to speak, say t plus 1 simplified, this is f ij, yeah, the pre-collision state mx and my at the previous time step, or we could say this is the post-collision state at the previous time step, and the post-collision state, so this is the streaming, this is the push streaming, yeah, and the post-collision states we simply compute locally by applying the Bgk operator that we already implemented above. So by combining these two things together, we can do with only one loop. Yeah, so we do not need to process our system twice, but we compute locally the post-collision distribution, and then we shift it by I and j to the pre-collision distribution in the next time step. So in order for this to work, we need, of course, these two sets of distributions. So we write which direction did we do it? So we we take A, we take the data from A, and then we put it into B. Yeah, so the next time step, they will be the other way around. So what we need to do in the next time step is we have to replace these names so that now this here is B and this here is A, so that information goes this way, right? And then we have a system that is AB to BA to AB to BA, where these two arrays always change their name, and by so doing we can implement the streaming inside the collision. There are much more efficient ways to do this, but this is a relatively simple and method that works. So okay, this is the bulk system which we have now processed. Actually, two of them. If geo bulk here. So now the next thing is if geo mx my is equal to bounce back, and okay, we need the same loop, so I'm going to just copy this. So, and what we do here is what we introduced in the lecture as a delayed bounce back. So we very simply say that this new distribution, so we do it the same way. I should give here some space. Yeah, so we again want to have this distribution here. And what bounce back does on this node, it just inverses all the directions. Okay, so the inverse direction means that we get, instead of I, we get minus I, and instead of JJ, we get minus JJ. And here, this is the local position, and this again comes out of the A version of this, and this closes everything. I think I should do some semicolon here. So last one. Okay, I now simplify my life in copying this. The last boundary condition that we have is equilibrium. So, and we call this EIQ. So, okay, so this is the equilibrium. Again, we have to fill this guy, and instead of doing this way, now we said that this is the F equilibrium. II JJ of U MX MY V MX MY and rho MX MY. So there is one more that I need to close. Right. Okay, so this finished this, and then we close our loop over the geometry. So as I just said, we have to switch from the A to the B, from A and B to B to A. So this is called AB pattern. And we do this by exchanging the variables step A and step B. Step A and step B, by saying that step A and step B, this is nice, we can do this in Mathematica like this, is step B and step A. So all this does is exchanging these two variables. And this closes the time step loop. Okay, so now we have the time step loop. Now we want to save our data, and this we do by append to the data set row t. We append the data from row, and we do this for all lines. Okay, I'm not supposed to make any mistakes today. Okay, append to ut u. This is mistyped, append to. And again, append to bt we. Okay, so let me see. So this in principle closes our system. Okay, now I want to, because this was going to be a slow code, I want to introduce some monitoring device here that produces us a progress bar, hopefully. So I put here monitor, so this is not extremely important to understand this. This is just helping us monitor. Okay, so I put here two monitors, and these two monitors are supposed to give us a progress indicator of T out, T, this is written T out, and from 0 to out steps. And again, and another progress indicator for T and 0 and steps. So let us see whether this actually, I'm not sure about this brackets. Okay, let's save it. So it states that the brackets are okay. So apparently, so if this now works, then it's our Lattice Boltzmann code. We'll try to run it only for a few time steps now. Run LBM, say 10 cycles of each 10 time steps, and now is 0, 0. Okay, so I see. Abort evaluation. So it never, you know, this would be completely crazy because it never runs. It never runs the first time. Oh. Progress indicator. Okay, let's just make things small. Ah, wait, here. There's the wrong velocity here. This is still null. By the way, this is also, but there was obviously a problem here. However, this problem should not have stopped the code from running. Okay, we're doing some post-processing because we are running out of time, and because the post-processing is not so important for the code. I'm just saying, okay, I take this from my cheat sheet, and this generates a field of all the nodes where we have bounce back and produces a rectangle there. And then we display the velocity field, which now is just because I stopped the collision operator. It will just be the initial condition. Okay, here we go. So I've forgotten to count up I in this loop. And because I copied it, I forgot it 3 times. Okay, now let us see whether this works. There's still the null. Okay, apparently I really had a bad night after my vaccination yesterday. So the actual problem is that if has to be written with a lowercase f every time here, and I mistyped this, and because I mistyped this Mathematica code didn't run. So I now corrected this one, and we set again new initial conditions. We empty our data storage, and then we run our code. And now we do our post-processing again, and this is the velocity field that we get out, and this we get for a pressure wave that's going around. Okay, so this was a little bit suboptimal, that I couldn't find this mistake during the lecture. Now we've fixed it, and actually we finally arrived at our Lattice Boltzmann solver that can now also be run for longer time steps, of course, but it's of course a slow code. So again, this here is the code that we finally came up with. Thank you very much for listening, and see you next year.